All right, we've seen the derivation of motion estimation, and now let's put it to practice. Let's write some code. Let me remind you where we left off. The motion v, vector valued, two values, vx, vy, at every pixel in the image is equal to, can be estimated rather as the negative, that was the minus sign that just got lugged over from the least squares estimation, of this, the inverse of this little 2x2 matrix that has the spatial derivatives in it. We still have to worry about when this is invertible, and we'll come back to that in a little bit, times this little vector here that has a combination of horizontal and temporal derivatives all integrated over these little patches omega. So what we need to figure out, so we derived this, let's put that behind us now. What we need to figure out is how do we compute these derivatives? Now, we know how to compute x and y derivatives, but we have this sort of extra dimension here, t. So let's go back to these spatial derivatives. Let's say I have two moments in time, frame 1, frame 2. And I would like to estimate for each pixel in this sequence how much motion there was between the frames. So do I compute the x derivative in the first frame or the second frame? And now the temporal derivative, maybe that's a little bit more obvious. I just take a difference between those two things because that's a simple temporal derivative. The right thing to do here is to take these two frames and average them, 0.5, 0.5 of each, and then compute the spatial derivative from that. The reason for this, we've actually already seen, and so let me just go ahead and remind you. When we were talking about the proper way to compute derivatives, remember I said that there's two derivatives. There's a pre-filter, a little averager, and then there's a derivative. And there's a derivative filter. And what we said is, in order to compute an x derivative, you differentiate in x and you pre-filter in y, that little low pass or average filter. When there are three dimensions, x, y, t, space, time, you, same thing, differentiate in x, pre-filter in time, that's the averaging that I just did right there, and then pre-filter or average in y. And so that's the reason why we take the average of these two frames, 0.5, 0.5, and now I have two filters, -1, 1, 0.5, 0.5. Why just these two-tap filters? Why only two values? Why not that nice five-tap, five values that I showed you earlier on when we were computing gradients? The reason is I've only got two moments in time right now. Now, you could say, well, I've got a temporal sequence. Why don't I look at 7 frames or 5 frames? We'll do that eventually, but right now let's assume we're computing motion just from the pair of frames. And now all I can do is compute a derivative using -1, 1. We've seen that before. That was the finite differences because I've only got 2 moments in time. And so I've got to use the same set of filters in space and time. So here are my two filters. -1, 1, 0.5, 0.5. One is a derivative filter, D. One is a pre-filter, which is just a simple averager. And now the way I compute the x derivative is I average the two moments in time, f1 and f2. So that's applying essentially the pre-filter, 0.5, 0.5. I differentiate in x, and then I pre-filter in y. Okay, there it is right there. Now, what is the y derivative? Well, it's going to be pretty similar. What am I going to do? I'm going to take the same difference, 0.5, 0.5, and then I'm going to differentiate in y and pre-filter in x. And what I get are these two images here, which are the spatial derivative of that average. And you can sort of see that. One tells you rate of change in the horizontal direction, one tells you rate of change in the y direction of that temporally averaged image. So that's good news. I now have my x and y derivatives here for this little 2x2 matrix, which I'm going to have to invert. Now, where do I get the temporal derivatives from that I need for this little guy right here? Well, let's go ahead and compute that. Well, the temporal derivative says differentiate in time and then apply the pre-filter p in x and y. So I take my two images and I difference them, which is this right here, and then I do a little pre-filtering, px and py in each of the horizontal directions. Notice the symmetry here. Every derivative, fx, had 3 filters. Average in time, average in y, differentiate in x. The y derivative. Differentiate in y, average in x, average in time. Temporal derivative. Differentiate in time, average in x, average in y. That's that same concept that we saw earlier on, just extended into the temporal domain. And now I have everything I need. I've got my x derivatives, I've got my y derivatives, and now I just need to compute little summations over little patches, 3 by 3, 5 by 5, 7 by 7, whatever you want. Pack everything into this little matrix in this little vector, invert, multiply, and I get an estimate of motion. Now, coming back to the same question, when is this matrix going to be invertible? More importantly, when is it not going to be invertible? Anytime you invert a matrix, you'd better be thinking about the invertibility of it. And so let's just think a little bit about what's going to happen to this matrix over here. So let's imagine the center dot right here. So this is just, imagine you have a little blue triangle on a black background that is translating. And I want to compute the x derivative in that little red dot in the center of a uniform blue patch. Well, what is the x derivative right there? Well, it's 0. There's no rate of change in the horizontal direction. What's the y derivative? 0. All right, now let's go back to the 2 by 2 matrix. If I sum all the x derivatives and all the y derivatives over a uniform patch, what is this matrix going to be? 0, 0, 0, 0. That is the mother of all rank deficient matrices. So I will not be able to invert or estimate motion in a uniform patch. Does that make sense, by the way? Of course. Imagine I had a huge white piece of paper in front of me, and all you could see was the paper, and you couldn't see the boundaries. And I was sliding it back and forth like this. If it was a uniform image, move up, move down, move left, move right, you can't tell. There's nothing on that piece of paper that tells you that there's motion because the intensity of everything is the same, and that's embodied in these gradients. Now let's imagine we've got a little patch right here where the x derivative is 0 in the horizontal direction, but the y derivative is not. Any better? Well, let's see. If the x derivative is 0, well then the first term here is 0, and the off-diagonal terms are 0 because the fx is 0 everywhere, which means I have 0, 0, 0, and then some non-zero value. Ooh, that's still rank deficient because I have a whole row of zeros. That's rank 1 matrix, still not invertible. So same thing with any oriented edge because there is only a rate of change in one direction. Your friend in estimating derivatives in order to invert this matrix are things that are at corners where there is a distinctive pattern both in the x and the y direction, and it will be invertible there. Now, what do we do here? Well, we just need to make sure when we're doing motion estimation, we check the invertibility of this matrix and make sure that when it is not well conditioned, it's either rank deficient or poorly conditioned, that we just don't make an estimate. We say, look, we don't know what's going on here and we're going to skip that. And I'll show you what that looks like in the code when we go to implement it. All right, so let's write some code. All right, so this is going to be a so-called 2-frame motion estimation. 2 frames because I'm going to take moment in time 1, moment in time 2. And then I'm going to go from time 2 to time 3 to time 4, et cetera, et cetera. So I'm going to take a sliding window in time, 2 frames at a time, and I'm going to estimate motion at the beginning, and then at the next frame, and the next frame, and the next frame, and then I'll get a sense of the motion across the series, the temporal series. Let's import a bunch of things here, and let's go ahead and I'm just going to load in 2 images. I won't do the whole series now because basically once you do 2 images, you do everything the same. You just keep loading in frames. Load in 2 images, and let's append them into a simple data structure. All right, here's the equation just to remind you. Velocity is equal to the inverse of this matrix with spatial derivatives times this vector with a combination of temporal and spatial derivatives. So now what we have to do is just compute these derivatives. And we know how to do that. Let me go ahead and define my 2 derivative filters. I've got 0.5, 0.5, that's the pre-filter, and I've got -1, 1, that's the derivative filter. And I can't do any better than that because I'm assuming a 2-frame temporal sequence. So now we have to compute a bunch of derivatives, fx, fy, ft. All right, what is fx? Pre-filter in time, pre-filter in y, differentiate in x. That's what this line does right here. What's the y derivative? Pre-filter in time, 0.5, 0.5, pre-filter in x, differentiate in y. Good, temporal derivative, differentiate in time, 1 minus 1, that's what the derivative filter is. And by the way, I'm not doing this as a convolution because I just have the 2 frames, so I may as well just add them together, add or subtract them. And then pre-filter in p in x and y. So now I have at every pixel, fx, fy, ft. I have the components to do this. And what do I want to do now? I want to just average over a little neighborhood, 5 by 5, 7 by 7, whatever it is. And the way I'm going to do that averaging is with a little convolution. I could do this in a couple of ways. I could have written a couple of for loops that went in and grabbed a pixel and averaged all the values. But what is the convolving with this little filter in both the x and the y do? It's a little average filter. So this is our favorite averaging filter, 1/16, 4/16, 6/16, 4/16, 1/16. Those numerators sum to 1. So this is a little averaging filter. And notice that it's weighted. Now up here, I didn't say anything about weighted. So you could have made it uniform. You could have made that 1/5, 1/5, 1/5, 1/5, 1/5. Or you can emphasize the center of that patch more than the peripheral just because it's near the center of where we're doing the motion estimation. Either way, we're gonna convolve our various quantities in the matrix and in the vector. So we've got fx squared, fx fy, fy squared, fxt, fyt. So that's what you see down here, fx squared, fy squared, fx fy, fx ft, fy ft. I convolve in the x and y direction with my spatial averaging filter, h, and now I have the quantity in each of these elements in my matrix and each of the elements in my vector. And I've just done that using the convolution trick here. And now I'm almost home, except we need a couple of tricks here. So what did I do? I loaded in the image, I computed the space-time derivatives, I computed those little averages through the summation, and now I'm ready to estimate motion. So let me initialize my Vx, Vy. That's going to be my motion estimated at every pixel. I'm going to subsample by a factor of 2 just because computing velocity to every single pixel is very tedious and often not necessary because we're assuming that the local motion is constant anyway. And now I'm ready to go. I'm going to build my little 2 by 2 matrix M. Here it is right here. I don't know why I changed that from A. So I've got fx2, fxy, fxy, fy2. Already I've done the averaging. That was the convolution up top. I've got my little vector right there. And now let's just make sure I can invert that matrix. So I'm going to check the conditioning of the matrix. If it's less than or equal to, I just picked an arbitrary threshold of 100. And I'm adding another constraint here that says that the gradient, that's what you see right here, is greater than some arbitrary threshold, which means I have a strong gradient signal. This is just a little trick that I put in to make sure I get reliable estimates where there is a strong gradient. Then please invert the matrix and then pull out V0, V1, which are the 2 components of the velocity, and then keep doing that over and over and over again for every pixel, or every other pixel in this case, because I'm incrementing by 2 in the image. Now, this is where the theory in some ways meets the reality. So I could have just displayed this for you, but motion estimation is hard, and it turns out to be typically fairly noisy. And so I'm going to do a little post-processing just to clean things up. And the post-processing here is going to be a median filter to remove outliers. Despite checking the conditioning, despite checking the gradient to make sure I have a reliable signal, you invariably get these little messy results. And so what we're going to do is we're going to do a little median filtering just to make sure that we get any outliers out. And think about that as a little averaging, but the median because we get rid of the outliers. And notice this little thing here where I've inverted Vy. This is because in the image, the y direction goes down, but I'm assuming it goes up because of the way I computed the derivative. So I just had to flip the sign of the y velocity. And now I'm going to use quiver to superimpose on top of the image the estimated vector field. Phew, that was a lot. And here it is. So let's see what are we looking at here. This is one of the 2 frames. I'm obviously only going to show you one. And superimposed on that are these little yellow vectors that show me the motion. So notice that the car right here is moving inward. And so the vectors are going in that direction. The car on the other side is moving also inward. And then, of course, the car is going around the corner. You see all the little motion vectors along the car showing a rotation motion. Notice, by the way, that you don't see motion anywhere else. Well, there's a couple of things going on here. In my quiver plot, I said that if the magnitude of I estimated motion at every pixel. But I said if the magnitude of the motion is small, then just don't display it. And then, of course, all the uniform patches in intensity where either the gradient was low or the conditioning was too high, I eliminated from consideration. So I'm only plotting where I can make a reliable estimate of motion. I'd rather have a sparse representation of reliable measurements than a dense representation of noisy measurements. And that's why you only see it in those few places where you can make reliable estimates. Now, one last thing we have to consider. I've been emphasizing that we're doing a two-frame motion estimation, time 1, time 2. There's nothing fundamentally limiting us to that. If I have, for example, that sequence of the taxi is multiple frames, I could have tried to compute space-time derivatives over 3 frames, 4 frames, 5 frames, or more. And the more frames I have, the more reliable those derivative estimates are. But there's another really interesting issue here, which I'm going to represent in this slide here. So what you're seeing here is a XT slice. So think about, instead of X, Y, T, the image changing over time, just a single scan line changing over time. And what I'm showing you up top here is at the bottom is like imagine two little blue squares. And what's happening over time is that they're shifting to the side. Okay? So time is unfolding. So if those blue squares, if nothing was moving, then they would just be lined up perfectly because in time, nothing changes. So by going like this, they are moving, right? Their spatial location changes over time. Now, what happens if they're moving faster? Well, then the angle of that increases. Why? Well, because between time 0 and 1, it moved a lot versus moving a little, a little, a little. Now, what happens when we have really fast motion? So this little 2-tap derivative, only looking in time, can only see things, that's that little red box here, that occur within a relatively slow amount of motion, right? So why is that? Imagine you have a little sensor right here on my forehead, and you're asking, what is the rate of change? So if I start moving like this, you'll be able to see my motion. But if I move like this, you won't be able to see the motion because it just, from time 1 to time 2, it just disappeared. It's literally like I shape-shifted, and that's no good. So these filters, our derivative filters, need to be able to see the motion. And if we only have 2x2 filters, because we're only looking at 2 moments in time, we're going to have problem when things start moving fast because they zap out of view. And so we have a couple of options. One option is we can use bigger filters. So look over a 7x7 patch instead of a 2x2 patch. Now, computationally, that's more demanding, but fundamentally, nothing changes. All it changes is the nature of the derivative filters. So going back to this paper again, Fried and Simoncelli, the differentiation of discrete multidimensional signals that we talked about earlier, here are your 7-tap filters for pre-filters and derivatives. And now the way you estimate the derivatives is you load in not 2 frames, but 7 frames, and you use this pre-filter to average them. So the first frame gets multiplied by this, the second frame gets multiplied by this, and so on and so forth. And then that gives you the average of all those, gives you a single image out, and then you compute X and Y derivatives there, and so on and so forth. So everything sort of looks the same, except now you have this bigger volume in space and time to integrate over, and you can catch things that are moving both slowly and quickly. And so this little code here is just computing the temporal derivatives. So this is just taking that weighted average of each of the frames of the video sequence and then doing the separable derivative filters to compute fx, fy, and ft, the same as before. And then the other option there is, so that will give you more reliable estimates of motion when things are moving quickly. Now the other way to do it is we've actually already seen it. So you remember when we talked about Gaussian pyramids? So here's my Gaussian pyramid of my 2 frames. So let's say, for example, you don't want the computational lift of computing these 7-tap derivatives and looking over 7 frames. Well, if I have a big motion here, what is the motion going to be here? Well, half, because I've reduced the number of pixels by a factor of 2. And what's the amount of motion here? 4. Right? So imagine something was moving 4 pixels here, it only moved 2 pixels here, and it only moved 1 pixel here. So the so-called multi-scale differential motion estimation says, start at the smallest scale with your tiny little filters, very, very efficient, and estimate motion. and then warp one of the images according to that motion estimation to make them more aligned. And then estimate motion at the next level, and the next level, and the next level. So up here at the top of the pyramid, you can do very coarse but not very accurate, and then you keep warping the images to get more and more in line, not perfectly, but you are reducing some of that motion. And then as you work your way through that Gaussian pyramid, you can always work with 2 frames and these small derivatives and not worry about these really big motions that are invisible to the derivative filters. Okay, so lots of things going on here. Let's separate out the math from the computation. The math is relatively straightforward. You have the brightness constancy assumption and the assumption that motion in a small patch is constant. From that, we derive the differential motion estimation, which is compute that little 2x2 matrix with spatial derivatives, the little 2x1 vector with space-time derivatives, and invert and repeat. And then there's a couple of bells and whistles. You got to check the conditioning of the matrix. You've got to make sure you're in a part of the image with a reliable signal, so the gradient of the image is high. And then you can get these nice little differential estimates of motion. We have to worry about fast motion because if the object moves outside of the scope of the derivative, we are blind to it. And you can solve that in 2 ways. Deal with more moments in time. Instead of 2, go to 7, go to 9, go to 11. But computationally, that becomes demanding. Or you can do everything inside of a Gaussian pyramid and then work your way through the pyramid with small filters, computationally efficient, but then you've got to make your way through a pyramid. Now, that was all differential motion. We started all of this by talking about 2 ways of estimating motion, feature tracking and differential. So now what we're going to do next is talk about feature tracking, and then we'll compare and contrast the 2.